So as I alluded to in a clip, a few clips back, the whole point of chapter 16 is we want to be able to integrate vector quantities over curves and surfaces and solid regions. And it turns out that the way that we do that computationally is breaking the vector down into components so that we're once again integrating scalar functions, because that's something that we already know how to do. So just to sort of recap the sort of things that we have in different dimensions, just to see sort of what the common thread of what's going on here, I'm going to write down a bunch of formal notation to draw out the parallels. So first off, think about the integral over a good old-fashioned interval. So this is back in Calc 2. We have the integral from a to b of f of x dx. And then when you do a change of variables or a change of parameters, you're going from u of a to u of b, and then you have f of u of x, and then you have du, right? Okay, and so here in this case, you didn't think of this at the time when you first learned u substitution, but that du there, the du is the length element under the reparameterization. At the time you just learned it as, oh, chain rule requires like you have to have the thingy or like it doesn't work, right? But what it's doing there is it's taking into account the fact that with the reparameterization, you're moving through the interval perhaps at varying speeds. And so that affects what's going on with the integrand. Then we also have the integral over a two-dimensional region. Whoops. I'll just call it a 2 region for short because I'm a lazy sucker. So this is the integral over r of now 2 variables. And we have, that's with respect to d area, some area element. And when we do a change of variables here to reparameterize and switch so that the integral is now over the parameter domain d, then we have f of, and say we're doing polar, so x is now a function of r and theta, where r and theta move through the d domain, and y is also a function of r and theta. And then we have this r dr d theta. And so now this guy is going to be our new area element. Whoops, area, if I can spell. Okay. And then we looked at triple integrals, which I'll just call an integral over a 3 region. And in this scenario, so we have, say, a triple integral. We've got f as a function of x, y, and z. And now it's d volume. And so say if we were setting this up, we were doing a change of variables like maybe spherical, then we would change this to a triple integral again over the parameter domain d. And we've got f of x as a function of rho, phi, and theta, and y as a function of rho, phi, and theta, and z as a function of rho, phi, and theta. And now we have rho squared sine phi d rho, d phi, d theta, and we have this whole guy as our volume element. And so you've seen some of this element nonsense before, like when we were also talking about integrals for arc length and surface area, right? So now we've got the same kind of idea, but the thing is we're going to be looking at the integral over a path in space, or a curve. So let C be a curve in, say, R2. Then we're going to need to have an arc length element. So I'm going to take, so when I say let capital C be a curve right here, when I write it with the capital letter, this is kind of like a, this is the notation for a set. So it's actually for, you know, some figure. So if we had this, then the green, okay, shoot, I drew everything in green, that was bad. Let me see if I can switch that real fast. Okay, so the green curve, that's what I mean, just that set of points. As opposed to, we can also think of a curve as a parametrized path. So let little c be a mapping from an interval AB into R2. And so this is going to be a parametrization of this curve, C. So that means we have C of t is going to have a first coordinate function and a second coordinate function. And t is going to live in this parameter interval, right? So what we're going to be talking about is the integral over a curve. So we just finished talking about like what it looks like when we have, you know, the integral over a region. Where's my shading? Here we go. The integral over a region, right, in R2. Now we're just going to be looking at the integral over this one-dimensional curve in R2 instead of this two-dimensional region in R2. So the integral over the curve of f, and we use ds to signify the arc length element. So this means in terms of the parametrization, we have the integral from a to b f of, and now where are we? We're at a point on the curve as parameterized by c, because c of t traces out that curve. And then we're going to need to have the arc length element, which is the, oh, sorry, I forgot. This book uses, I think, single bars for the magnitude of a vector, which is this guy. So this one here is the arc length element. And I think it probably makes the most sense if we just back up and say, hey, suppose for the moment that the integrand was 1. So then you would say, okay, so if we were just integrating 1 with respect to ds, then what do we have here? Well, we have from a to b, we have the function 1 times, and so I can just get rid of it, magnitude c prime of t dt. So now, what is this? This is the integral of the speed that you're going at time t times dt, right? Because this part right here is the velocity and speed is the magnitude of velocity. So this is just going to be a setup for the length of the interval, or sorry, the length of the curve c that you travel down. So this is just coming from this is the non-constant version of speed times time equals distance or length, same thing, right? Okay, so you can think of this integral then as being something like, hey, how much fuel did you burn? So this f might be non-constant because maybe if you're going up a hill, it's got a higher value because you're really burning the fuel, and if you're coming down the hill, who knows, maybe it's got a value close to 0, something like that. So this is our setup, and so when we write it out, it's going to look like a to b f of x of t, y of t, z of t, and then we've got the whole formula for the speed here. So x prime squared plus y prime squared plus z prime squared, and then we take the whole stinking square root dt. So that's the whole thing. So I will refer to this from time to time as like, this is what it looks like in the parametrized form, and then this is the one that it looks like when it's in the form that where we're actually showing what's going on with the coordinates of that parametrization. Okay, and the key point is this whole clip is all about defining this idea of ds, which is magnitude c prime t dt in a parametrization, right? So this makes sense without a parametrization. This only makes sense if you've chosen a parametrization c. And so this guy is the length element along the curve. Or, more commonly called, the arc length element. Or some books might call it the infinitesimal arc length, whatever. Oh, and I just realized I forgot to mention earlier, when I was talking about this right here, integrating 1 over a curve gives you the length of the curve. That should be real familiar as the one-dimensional version of integrating 1 over a region gives you the area, right? Remember that guy? And integrating 1 over a solid region gives you the volume of that region, right? So these are all the same.